of this year. So welcome. So now today Partha will be continuing his lectures on asymptotic symmetries and celestial holography. Take it away, Partha.
Yeah, so what we did yesterday is that we classified the one particle states under the inhomogeneous Lorentz group, which is ISO 1,3. And I mean, like, we started with the eigen states of the 4 momentum operator, and then we saw how they form a representation under the SO 1,3. And then actually we showed the isomorphism between these two groups, the Lorentz group SO 1,3 and SL2C. Right. So these are the group of Lorentz transformations. So they are like represented by 4x4 matrices, and they are represented by 2x2 matrices. Okay. And so now the basis that we talked about, so they transform nicely under SO 1,3, but they don't have nice transformation property under SL2C. Right? So then the next like natural move should be like to find a basis which transform nicely under the SL2C. So this is what we are going to do today. Okay. Okay. So let us now introduce a new basis, say for example delta sigma. Okay, so before that actually I want to like recall something from yesterday. So if you remember that I said that I will only be talking about the massless particle in 4 space-time dimension, and any massless particle in 4 space-time dimensions, so their momentum is null, and any null momentum can be parameterized using the 3 variables. So they were like E and Z bar. So and this ZZ bar, they basically parameterize the direction of all possible null momentum, I mean the space of all possible null momentum direction, and we call that as celestial sphere. So the picture is something like this. So this is the P0 direction in momentum space. Suppose this is the spatial direction. If this is the null cone, so all the massless particles, I mean like the momentum of all the massless particle have to lie on this null cone. So if you take any space like cart on this null cone,
Space, like it should be just, it should not include one of the axes. It cannot go to 0, right?
why not? So okay, I mean this is the momentum space picture, right? So okay, so the equation is p square equal to 0, right? Okay, so let me just show why this ZZ bar, they are basically actually the coordinates on the, they are basically called the strographic coordinates on this sphere. So why is that so? So this equation you can write it in this way. Now for a fixed p, this equation becomes some p1 by p0 square and you can define new variables, something like say x1 square plus, sorry, this is 1 plus x2 square plus x3 square equal to 1 for a fixed p0, right? So this is the equation of a 2 sphere. This is what I am talking about. So this is this sphere, and Suppose you are projecting it to a plane, so it depends like from which pole actually you are projecting, right? So if you are projecting from north pole, I think this should be like 1 plus x3. This z bar is x1 minus ix2, x3. Okay. And if you just replace this x1 by p1 plus p0, then you will see that the z bar that I had written yesterday, they will be something like p1 plus ip2 by p0 plus p3, and the z bar will be p1 minus ip2 by this thing. Okay. Now remember that the value of p0, it does not matter. I can take the card here or I mean like anywhere. Okay. So what matters is only the direction of this null momentum, and this z bar, they basically parameterize the space of all possible direction. So I will call the celestial sphere, I call this sphere the celestial sphere, okay, which is parameterized by these complex variables z and z bar.
Is the same parameters are running them used for this software?
Yes. Okay. Okay. So now, so the concept of celestial sphere is fine, right, from this momentum space. Okay. So now let me introduce a new basis. Delta sigma z bar equals to say n delta z bar This is called some conformal primary basis. Remember, when I am writing P, you should always think in this way. P is like written in this way in terms of E, Z and Z bar. So this integral transformation, this is something called the Mellin transformation. I think it's double L, right? And this n delta z bar, this is some normalization factor which we will fix later. Okay. So you see, we have taken the one particle state in momentum space and we have Mellin transformed it. So E is integrated over. So what is left with is this z bar, and we have introduced a new variable like delta. Okay. So now we want to study what is the SL2C transformation property of this new state. Okay. Now actually yesterday, these 4x4 matrices I was calling them by lambda, and these 2x2 matrices I was calling them by m. But today actually both of these matrices I will call by lambda, because they are, I mean like when I will be talking about when I will write something like lambda, you should think that this is a SL2C matrix, 2x2 matrix. Okay. But sometimes I may tell that this is a Lorentz transformation, but you should think that that is actually an SL2C transformation, because they are basically equivalent. Okay. So what I want to study is what is U lambda.
There is information of P, the left hand side you should have a P, right?
No, P, okay, so what I told you that P is parameterized. So P you can write in terms of E, Z bar, and this E is integrated over. I have traded E for this delta. So now what, fine, right? So now what I want to study is what is the Lorentz transformation property of this state. Right? So now if you remember,
What information does sigma contain here? Any other
sigma is the helicity of the particle, right? Okay.
and -1 delta -1 just by for convention.
No, this is the Mellin transformation actually. So if you have a function, say f of x, so the Mellin transformation is defined in this way: dx x to the some z minus 1, 0 to infinity. This is the definition of the Mellin transformation. That depends actually. So in general actually this integral may not be convergent. So that will depend actually the real value of delta. Okay.
Right now
And
it's
so
general.
so
It is general.
okay, I mean like, so if this integral is not convergent, then we will introduce some, I mean we can just introduce some regulator and make that integral convergent, but that will not matter for this part of the discussion. Okay, and I mean like there is a strip of delta, I mean like for some real values of delta, say for example, suppose for these values of delta, if delta lies in this strip, then this integral is convergent, then this strip will be called the fundamental strip of the Mellin integral. But okay, I will talk about this actually in the later part of my talk. But for the time being, you don't have to worry about the convergence and like what is the value of the delta. Okay, so you just take that delta is any complex number.
Just one more question. So, does an inverse transform exist as well?
That will depend whether the integral is convergent or not. Okay, that I will talk in the second half. Okay. Okay, so we want to study the Lorentz transformation property of this state, and if you remember what we did yesterday was we started from some reference null momentum, and we actually found what is the little group of that reference null momentum. Here actually you see what matters is the direction, right? So today what we will find is what is the little group of the reference null direction. So my reference null direction in this case will be given by z equals 0, z bar equals 0. So I'll, okay, so what is z equals 0, z bar equals to 0 in the momentum in this form? So this is basically nothing but the p mu equals to e comma 0 comma 0 comma 0, right, because z and z bar is 0. So I'll just, what I'll do is that I'll try to find the reference null direction of this momentum. Okay, the little group of this reference null direction. Okay, so for z equals to z bar equals to 0, how does this state look like? So this looks like delta comma sigma is something like n delta 0 comma 0 some e comma. So what this is telling you is that if you have like if your null momenta, all the null momenta are directed towards the positive 3 axis, here E is greater than 0. Okay, so if your null momenta, if they are all of them are directed towards the positive 3 axis, then all those null momentum they are getting mapped to this particular point, z equals 0, z bar equals 0. Okay, and I want to find the little group of this reference null direction because the magnitude of E does not matter. Okay. Okay, so yesterday I calculated the little group for this null momentum 1 comma 0 comma 1. So they were actually ISO 1 comma t, ISO 1 comma 2, and they were generated by these three like generator A, B, and J3. Okay. So now today we have to add one more extra. I mean like okay, this is still a little group of this thing, right? That is clear, right? I mean like if you just apply this kind of transformation to this vector, it does not change. Okay, because AB anyway will give you 0 and J3 is the rotation in these two planes. So anyway this does not change this P mu. So today actually and today actually what I am saying is that this magnitude of E does not matter. So you can scale E by something, right? Say for example some e to the power minus eta into E, something like that. Then that will also be again element of the little group. Okay, because the direction does not change, only the magnitude changes. And if you remember that this happens under the boost in the third direction. Okay, so the boost in the third direction is the extra thing which enters into the little group of this reference null direction. Okay. Okay, so let me write down the action of all these generators. So then with this I have to include. So these are my Lorentz transformation which is keeping this direction invariant. Okay. So let me write down the action of all these things. So A is A acting on this delta comma sigma z equals to 0 So if A hits on this state, it will give you 0, and that is the same for B as well. What is the action of the J3? So U of say J3 is the rotation in 1, 2 plane. Let me call R of phi, say for example, acting on this delta sigma. That is like when it hits this state, it will just simply give you I sigma phi. This is also from yesterday's discussion, and so that implies U of R3 phi acting on delta sigma Z equals 0, Z bar equals 0, that is something e to the I sigma phi okay. And I told that there is one extra element, that is the boost in the third direction, okay, and the action of that boost is U of, say, let me call it B3 eta. Eta is called the rapidity, okay. So that will something n delta 0, 0. Okay, and this thing, you know what is this action? This action is nothing but E only gets changed, e to the minus eta E 0, 0. This you know already, right? The boost in the third direction only changes this momentum into this. Okay. Now you redefine a variable. You call e to the minus eta E is something like omega, and then you can change these things, and you will actually finally what you will see is that this thing will be like something like n delta 0, 0 e to the eta delta that is nothing but e to the eta delta okay. It's okay, right?
Yeah, so, I mean, this B3 is just to denote boost, right?
Yeah, just to denote boost, it's the boost in the third direction, and eta is the rapidity. Okay. So now I have written down the actions of all the little group generators on this state. So now actually I can calculate actually what is u lambda of delta sigma z z bar. Okay. So again I think actually if you remember from yesterday, so when I was calculating, this thing, so actually I have written this transformation in terms of the little group transformation, the same thing that I will again do it today. So say u lambda delta sigma z comma z bar, that is what I want to calculate. Yes.
The little group should be the same for any reference point.
Any reference null direction, yes. Yes.
So
No, actually here I am allowing E to vary, right? Yesterday I did not allow that. Yesterday my null momentum was like 1, 0, 1 and that 1 was fixed. I did not allow to vary it. Today actually I am allowing E to vary. So then that's why this boost in the third direction came into the picture. Because that is telling only about the information about the direction of the null momentum, and this is the null momentum. I mean, the magnitude also matters here, but their magnitude does not matter. Why K3 is element of the little group? Because it does not change, it does not change in the state in the sense that it does not change this point z equals to 0, z bar equals to 0. Because if you see, okay, so for example, under K3 transformation, so this vector, it is getting mapped to e to the minus eta e, right? Now you can calculate z and z bar, right? So z was like your p1 plus I p2 by p0 plus p3. So with this new null momentum also, it is 0, right? Similarly, z bar is also 0. So that means the K3, the action of K3, it is not changing this point z equals 0, z bar equals 0. Okay. And I am trying to find the little group of that point actually, z equals 0, z bar equals 0. Okay, so I was trying to find the action of Lorentz transformation, which is again equivalent to SL2C. So of this particular state. So this now I will write it something like this: U of lambda, say R z comma z bar, acting on this. Okay. Okay, you see, for example, if you start with this vector, which is nothing but actually, okay, so this state I have got from this null momentum e comma 0 comma e by Mellin integrating this null momentum, right? Now if you make a general rotation, okay, so this null momentum will look like e some e sin theta cos phi from the e cos theta, right? So basically this null momentum will get transformed into this null momentum, and the corresponding state would be delta sigma z bar. Okay. So starting from this particular state, if you make a rotation, arbitrary rotation, okay, see theta phi and z bar are equivalent. If you remember that relation, z equals to tan theta by 2 e to the I phi, z bar equals to tan theta by 2 e to the minus I phi. Then you can see, okay, so I mean like I can use theta phi or I can use the z bar. If I use the z bar, then this null momentum will look like actually that null momentum that I have written, p mu equals to that thing. Or in theta phi it looks like this. So what I am doing is that I am starting from this state, okay, or rather which is actually a map from this null momentum, okay. Then I am making a rotation, general rotation by an amount theta phi, or you can say by an amount z bar, to get this null momentum, which is basically again after Mellin transforming giving you this state, okay. So this state is nothing but related to this state by just an arbitrary amount of rotation. Is this point clear, right? So that's what I have written here, okay. So this state delta sigma z bar, it is related to the state by an arbitrary amount of rotation, okay. And this n delta z bar, it is normalization factor, okay.
So are you fixing n delta 0 0 into this something?
that I'll do it when I'll like what is it called? Well, I'll talk about the inner product actually. Okay.
You need a denominator here. Oh, one question. N delta 0, 0 in the denominator.
No, because actually I've introduced this n delta z z bar, right?
No, he's saying n delta 0, 0 in the denominator, so that the final normal
Okay.
is n delta.
Let me then actually. Okay, let me write. Okay, no, let me write this clearly actually. So you see delta sigma z equals 0, z bar equals to 0, that is like n delta 0 comma 0. And this delta sigma z comma z bar, it is just a rotation u r. Okay, and that is like in delta 0 comma 0. So this rotation hitting on this momentum, it is giving you this p comma sigma, right? I think I am right. And there will be some factor. So this factor included, I mean like this factor with this factor, which is what I am calling n delta z z bar. There will be some factor of 1 over z plus z bar or something like that actually, if you just actually. So this thing actually I have written in terms of the sine theta phi. When you will actually convert those theta phi into z z bar, there will be some factor, okay, and this whole thing actually I am calling it as z z bar. Yeah, so this is the thing, right?
Yeah, so then n delta z z bar should be included here. It will be n delta square. Because u was already acting.
So you are saying that I should divide by a factor of n delta 0 0. That is what you are saying.
From what you did right now,
Okay.
put one more n delta before u of r, you'll get n delta square. So we shouldn't put n delta.
Oh, I see. Sorry. I think okay. So I think it should be like 1 over n delta z z bar. Is that fine now?
Now there is no n delta.
I think. No, I think this is fine actually. This should be like n delta z z bar. I mean, okay. Huh.
In the equation that you're just writing,
Huh.
there is no u delta, u lambda, sorry. In just the equation.
This equation.
No, this equation.
Yes.
There is no u lambda.
Huh.
You are saying delta sigma z z bar is n delta times u times.
Yes. Yes.
In that equation, there is no, in the equation that you wrote down,
Hmm.
delta sigma z z bar is just u times that. There is no n delta z z bar there. So these two equations.
Oh, acha. Okay, sorry, yeah. So there should be n delta z z bar. Thank you. So then actually, okay, so then actually this thing will give you this p sigma, okay. So this factor actually, okay, so right now think about there is some factor, okay, and okay, so now, okay, let me do it clearly. So now there is this n delta z z bar. okay, and this is what I am telling you, that this should this thing actually I was writing is as n delta 0 comma 0 and then 0 to infinity d e to the delta minus 1, and this rotation will hit on this thing u of r. This is now fine, right?
But if I said z equal to 0,
You said
No.
equal to 0, u of r is identity.
identity.
No, this is not z equals 0. I have not written the z bar here. The z bar is there.
But suppose I choose the u of r to be identity,
Huh.
then that is just left hand side will just be delta sigma 0 0. The right hand side will have n delta 0 square.
Okay, okay. Huh. So now when, okay, so now when actually this rotation, okay, I now understand. You are saying that when I will say it, that I should get n delta square. Acha.
So I think if you just replace n delta z z bar by n delta z z bar by n delta 0 0, I think it should be.
Huh. So, okay, okay. So you are saying that if I divide it by n delta 0 0, then it's fine.
It should be fine.
Okay. Let's do that and let's see what we get. Okay. So u lambda. So suppose this n delta z comma z bar divided by n delta 0 comma 0, and then this u lambda and r, it will get multiplied and it will give you u of lambda r z comma z bar acting on this delta sigma z equals 0, z bar equals 0, right? Now I am writing an identity matrix in this way, that u of r inverse lambda z bar. If you remember my notation, my lambda z was the transform z, right? Lambda z was like az plus b plus by cz plus d, and lambda z bar is the corresponding bar thing. This u of r lambda z bar. Okay. Now you see what this thing. So this thing again I can write it as n delta z z bar u of r lambda z comma lambda z bar. Is u of r inverse lambda z bar. Okay. This u of r inverse. This just means that this is an inverse rotation by an amount lambda z and lambda z bar. Okay. If you want to call it like u inverse, I think you can do it. Okay. So r inverse lambda z bar, then lambda of r z comma z bar acting on this state delta sigma z equals 0, z bar equals 0. Now you see what this matrix element is doing. You see, first of all, this rotation z bar, it will take this state to this yeah. So now see, now just look at that matrix. So what is this doing? So first thing is the rotation by an amount z bar. Okay. So that will take you the point z equals to 0, z bar equals to 0 to an point z bar, right? And then there is this Lorentz transformation lambda. Okay. So that will take this point to lambda z bar. And then again there is an inverse rotation by an amount lambda z bar. Okay. So then that thing will again take you back to z equals 0, z bar equals 0. Okay. So then this matrix element is my little group matrix element because it is not changing the z equals 0 and z bar equals 0 point. Okay. So this is what I will call W. So W lambda z bar is now R inverse lambda z bar lambda R of z bar. Remember here lambda is A B C D with AD minus BC equals to 1. Is that clear? I mean, like, okay. So now actually you can explicitly calculate this little group matrix elements. So in terms of this little group matrix element, then my Lorentz transformation on this state looks like, it looks like n delta z bar by n delta 0, 0 u of r of lambda z bar u of w acting on delta sigma okay. Now I can explicitly calculate these little group matrix elements okay, just by multiplying these matrices because I know how does this matrix look like, all these matrices actually look like. Okay. So for example R of z bar, this is an rotation by an arbitrary amount of z bar. In matrix form it is like 1 over square root of 1 plus z bar 1 z minus z bar 1 okay, and this lambda I have already written, and then this R inverse lambda z bar, it will look like square root 1 plus lambda z bar 1 minus lambda z bar 1. So I have now given, like I have shown all the matrices here. So R z bar is given by this, lambda is given by this, and the inverse rotation is given by this. Now you can multiply all these three matrices and you can see what does this W look like. Okay. So this W will look like something like this. E to the say alpha by 2 0, 0 e to the minus alpha by 2, 1 0 beta 1 okay, where e to the alpha it is now given by 1 plus z bar by cz plus d square 1 plus lambda z bar okay, and the explicit form of this beta is not required okay. In SL2C terms this is a special conformal transformation, but if you think it from the Lorentz transformation perspective, it will basically give you the transformations which are generated by these two matrices A and B, and I think that is confirmed by Rito yesterday. So that's why actually the explicit form of this beta is not known, because anyway when this B will hit on this P sigma state, that will give you 0, and this delta sigma z bar, it is nothing but the Mellin transformation of those P states. Now since A B acting on those P states is 0, so A B acting on this delta sigma z bar is also 0 okay. So that's why I am not like interested in the explicit form of beta, but this is important. So e to the alpha is given by this this expression okay.
Can you repeat that? I didn't understand now. What was this decomposition and why you have?
So if you multiply these three matrices okay, and then you will get the W lambda z bar okay, you will see that that W can be decomposed in this way okay. now what I am saying is that this particular transformation 1 0 beta 1, this is the special conformal transformation in SL2C terms, right? But yesterday I told you, like given A, B, C, D, how can you calculate the 4 by 4 lambda matrices, right? Now if you calculate the 4 by 4 lambda matrices, what you will see that this thing basically generates the transformation in terms of Lorentz transformation. Those transformations were generated by A and B operators. Okay. Now what I am saying is that my delta sigma z equals 0 and z bar equals 0. So that is, I think that is related by the Mellin transformation to this E00 E state. Okay, now AB acting on this state is basically AB acting on this state, and yesterday I told that AB acting on this state is 0, even today also I think I have shown. So AB acting on this state is 0. So that's why this thing does not matter. Okay, the only thing that matters is this matrix e to the alpha, this diagonal matrix. Okay.
You mean to say you only require the form of this diagonal matrix?
Yes.
Where alpha is given.
Yes.
You don't have to care about what beta is.
Yes, exactly. Okay. So this is written in terms of the SL2C matrices, SL2C matrix. Now I just want to remind you that under what kind of transformations actually give you this diagonal diagonal form for these SL2C matrices. If you remember, that is the rotation in the third. Okay, actually I think I showed you the example. For example, rotation around this third axis u of r3 comma phi, that is given by e to the I phi by 2 0 0 e to the minus I phi by 2, and the boost along the third direction, it is given by e to the eta by 2 0 0 e to the minus eta by 2. These are the only two transformations for which which actually this W actually is diagonal. Okay, these are the only two transformations. All the rest, all the other transformations, this SL2C, all the other transformations, the SL2C matrices are not diagonal. Okay, like for example, if you take boost along the say along the x-axis, then these matrices will not be diagonal. Okay, so what I am trying to say is that since my little group matrix is now diagonal, so I have to find all the transformation under which SL2C matrices are diagonal. And I am telling you that there are only two transformations, the rotation around third axis and the boost along the third axis. So only under these two transformations, the SL2C matrices are diagonal. Okay. Hence, now if you multiply these two things, sorry, this should be R3 of phi. Oh, yeah. So now this, if you multiply these two things, R3 of phi, B3 of eta, so you will get this e to the I phi plus eta by 2 0 0 e to the minus I phi by 2 plus eta by 2. Okay. So I will need this information. Huh? Oh, minus is overall minus, yeah. Yes, yes. कहाँ चला गया उधर भाई? I have made a mistake here. Actually, where is that board? There should be a factor, normalization factor, n delta lambda z bar. Okay, yeah. And then again there will be a n delta 0 0. So these things I think will cancel because what is that board, man? No, this is not that board, no?
You erased it.
Oh, I erased it. Okay, fine. Okay, this is easy. I mean, like, so I was calculating this thing. Okay, and okay, so you have to believe me now. Actually, so this thing will happen. Okay. Okay. So, so then, I mean, want me to show this, or I mean, like, this is fine? Because actually when actually I applied this transformation, oh no, again sorry, I have not applied this transformation yet, right? That's why actually there is no this thing. Okay, so yeah. Actually when I will apply this thing, then actually this will happen. So I have not applied it yet. So okay, so this thing was like n delta 0 0. And then I have this u of r lambda z bar, and then you have this little group thing, and your little group thing was like there were 4 actually generators A, B, Z3 and K3. Okay, so that means you have this u of AB is anyway 0, so you have this u of K3 meaning the boost along the third direction, so I am writing this in this way, and this J3 meaning the rotation around third axis, R3 of phi. This is acting on delta sigma. This is fine, right? These are my little group matrix elements. Okay. So then this is like n delta z bar, n delta 0 comma 0, u of r lambda z bar, and this thing it will give you e to the I sigma phi, and this thing it will give you u of e to the eta into delta, right? Somewhere I had calculated this, right? What is the action of u of b3 eta? Somewhere I have calculated it. It will give you e to the power eta into delta. Okay, acting on this delta comma sigma. Okay. So this thing you write it as e to the power eta delta, e to the power I sigma phi, and then u of r lambda z bar acting on this state. So when r lambda z bar acting on this state, it will give you something like n delta 0 comma 0 by n delta lambda z bar, and under this rotation z will go to lambda z bar. Okay, hence finally it becomes like n delta z bar, n delta lambda z bar by delta sigma. Fine, right? Now you can actually actually compare this with this thing. Okay, so you see this e to the power I phi plus eta by 2, that has to be like actually this I phi plus eta has to be like equal to alpha. So eta plus I phi, it should be because that is my little group matrix. Okay, and that is also like the little group matrix. So eta plus I phi should be alpha, then eta minus I phi, it should be like alpha bar. So you can calculate what is your eta. Eta is like alpha plus alpha bar by 2, and then phi is
So both are giving same equation. I mean, there is some minus sign issue.
no, why? I mean like eta plus, both are giving the giving for eta plus alpha phi, but they are complex, right? I am just taking the bar, right? Eta and phi are real, alpha is complex. So then this is like minus I alpha minus alpha bar by 2. Did I make a mistake or what? No, this is fine, right? Okay, so so you just put that thing here. So n delta,
Sorry, why you are ignoring this part 1, 0, beta 1?
that's what I explained, like these are responsible for the generators so these are the special conformal transformation, right? And I have told you that if you just write this matrix in 4 by 4 form, it will see that you will see that they are responsible for these they will give you these two operators A and B. And this A, B, yesterday actually I told that for massless particles, when this A, B acting on this state E00 E comma sigma, it will give you 0 actually. I mean, because massless particle doesn't have continuous, that was my logic yesterday, doesn't have continuous degrees of freedom, so that's why this AB acting on the state should be 0. So that's why this particular matrix is not important for me. Okay?
Partha,
Huh.
so this R35 written there,
Huh.
that is like that's a unitary operator, na? मतलब exponential I J3 phi, that gives you that matrix. like R35 का जो this matrix is there, right?
This,
Yeah,
huh?
so this you got by exponential I phi J3 something like that, right?
I phi J3, I phi J3, yes.
So that's a unitary operator, no?
Huh?
So, but when you say U of R35, what do you mean by that? R35 itself a unitary
I mean,
operator?
U of R35 meaning, no, R35 is the matrix, right? I mean, it tells you like
No, but it's a
matrix
matrix, but
representation.
That's a different representation.
I mean-
R3 acts on the vectors. U of R3 acts on
The state actually, yeah. Okay, so this is like n delta. And this e to the power eta is now like alpha plus alpha bar by 2. So this you will get like e to the power delta into alpha plus alpha bar by 2 and e to the power I sigma, and phi is like minus I, so this I will cancel, so it is like alpha minus alpha bar by 2, and that is like delta sigma lambda z bar. So this will now become e to the delta plus sigma by 2 e to the alpha to the power into delta plus sigma by 2 and e to the alpha bar to the power delta minus sigma by 2. Okay. Now you remember the expression of e to the power alpha. This is the expression of the e to the power alpha. Okay. So you just put it there, substitute for e to the power alpha. So then u of lambda zz bar, that is equals to n delta zz bar n delta lambda z bar. So if you substitute for this e to the power alpha from that equation, so what you will get is that 1 plus lambda z bar to the power delta by 1 plus zz bar to the power delta 1 plus zz bar to the power delta 1 plus lambda z bar to the power delta, and then 1 over Cz plus d delta plus sigma 1 over Cz C bar z bar plus d bar delta minus sigma, and then this state delta sigma lambda z bar. Okay. Now when I will calculate the inner product, actually I will fix this normalization factor to be n delta zz bar, that will I will fix like 1 over 1 plus zz bar to the power delta. So if I fix my normalization factor like this, then u of lambda delta sigma z comma z bar goes like 1 over Cz plus d 2h 1 by C bar z bar plus d bar 2h bar delta sigma lambda z bar, where I have defined my h equals to delta plus sigma by 2 and h bar equals to delta minus sigma by 2. Okay. So you see, I mean, like how this state transforms. This is just a transformation property of the SL2C primary.
You started with the state in some spin, sorry, velocity sigma, right?
Hmm.
And you're doing a Lorentz transformation and the spin velocity doesn't change at all.
Helicity changes, meaning for massless particle it changes, it is actually like e to the power I sigma thing, right, under Lorentz transformation for massless particle.
So I actually have a consequent question. I mean, you are doing a Mellin transform and ending up with something which looks like
Yes, yes.
strict transforms under
Mm-hmm.
how as primary transform.
Yeah.
But one could have chosen to do some other transformation and gotten some other kind of way. Like, what's so special about the Mellin transform in this case? Like,
I mean, okay, so for this, I mean, I started with that isomorphism, right, SL2C.
Yeah.
So I want that my state should transform covariantly under like SL2C, right? So now I think, okay, I mean, like Mellin transformation is doing this job for me. Now you are saying that if instead of Mellin I do some other kind of thing, that may not like give you this transformation property, that may give something else that I don't know. Yeah. I mean, like my whole point was, since there is an isomorphism, so my whole point was like I want to find a basis where actually my state should transform covariantly under SL2C transformation. So if you have any doubt, you can now ask me. So you understood it, right? I just started with a one particle state in the momentum space. Then I make a Mellin transformation. I got this state delta sigma zz bar. Now what I have shown you that this state delta sigma zz bar under the SL2C transformation. Remember this lambda is SL2C matrices here. Under SL2C transformation, this state transforms like a primary operator in a 2D CFT. Okay.
Still didn't get clarified. When you act with the Lorentz transformation on a helicity state, don't you get a mixture of two velocities?
Actually, for massless particle, it does not happen in that way. For massive particle, actually, that is the thing.
So helicity is like the projection of the spin onto the momentum, right?
You can never.
You can never, you only going to change this if you change the momentum exactly opposite. I'll never.
for that you'll have to overtake the massive.
That's not with the Lorentz transform.
Yeah.
But these correlators, they form an algebra.
The little group. Yes, they form an algebra. I don't remember the commutators. So the extra thing is the boost in the third direction K3, but you can see that they form a closed algebra actually. I think J3 and K3 commutes with each other, right? I think they should commute with each other, and K3 will A and B, they will give like A and B again.
So, Partha, just a quick question. In the earlier, so you had this beta, which was the special, which you said
Ah.
like the special conformal
Hmm.
transformation. Suppose I didn't do either the boost in the third direction and the rotation in the third direction.
Okay.
I just do a special conformal transformation. Is identity on the state, is it?
I think I don't understand most
So
probably.
you wrote, so in that equation above,
Huh.
the u of B3 and R3.
Huh.
So in earlier it was u of W,
U of W.
right? So if if the beta part was not did not do anything,
Huh.
then I am saying that I replace it just B3 times R3. That W.
Because my little group matrices like are the 4 elements, right? A, B, B3 and R3, right? Sorry, A, B, K3 and J3, right?
Correct. So I'm just
Huh.
stating, if I let's say have alpha is 0, I choose a transformation, little group transformation, where for me alpha is 0. Like there's no.
That you cannot do, right? Because that is, I mean, like you have to first like find out what is your little group transformation given a reference null direction. That will automatically come out. I mean, like how can you say alpha equals 0? How can you set alpha equals 0?
Choose my own little group transformation. Like I can do.
The little group is, once you choose the reference null direction, little group is fixed, right?
Little group is fixed. I'm saying a particular. So let's say I'm not doing a Lorentz transformation on the state. Okay, instead of u of lambda on a state, I want to do u of w on a state.
Yes.
Okay, so now in the w is my choice. I can choose whatever w element of the w I want, right? I mean the little group is ISO2. That is fixed.
How can you choose? I mean, like that is like some transformation. So the matrices are also fixed, right? This is some transformation. So matrices are also
No,
fixed.
the matrix type is fixed, right? It's up to me what lambda I choose, right? You're saying that there exists no lambda where I can get only special conformal transformation?
No, 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 no. That is not possible. Then there is no meaning. It is trivial, right?
Sorry?
Then there is no meaning. It is trivial transformation.
That's why I'm asking.
But that is, I mean, like okay. So I mean, like you are saying that under an identity transformation, a state should remain same. I mean, like that's it most probably.
Right.
Okay, so now actually I should calculate the inner product. Okay. So okay, so my delta sigma z bar, that is given by okay. So now I want to calculate the inner product between these two states. So what I want to calculate is this thing, delta 1 sigma 1 z1 bar that should give you something like in delta 1 star z1 bar in delta 2 z2 z bar 2, okay, and then this thing integration 0 to infinity dE1 E1 to the delta 1 star minus 1, so integration 0 to infinity dE2 E2 delta 2 minus 1, and then P1 sigma 1 P2 sigma 2. Okay. Now you know what is the inner product between the Fock space states. So P1 sigma 1 P2 sigma 2, these are basically 2 pi q is mod P1 delta q P1 minus P2. Okay. So what you have to do is that that parameterization, okay, I don't have. So you had this parameterization, P mu equals to, P mu is in terms of E and Z bar. Okay. So you have to like write down every P1 and P2 in terms of the Z1 and Z2, and then you have to substitute this inner product in this thing, and you have to integrate. I mean, like you have to integrate actually this thing. So there will be this 3 delta function. It will become like delta of E1 minus E2. So one E1 integral you can do, and the other thing will become like delta 2 of Z1 minus Z2. What this delta 2 of Z1 Z2 meaning delta of this particular thing, that means delta of real Z1 minus real Z2, delta of imaginary Z1 minus imaginary Z2. Okay. So now if you substitute it back into this equation, so what you will get is that n delta 1 star Z1 bar 1 plus Z1 bar to the delta 1 star, then n delta 2 Z2 Z bar 2 1 plus Z2 Z bar 2 to the delta 2. Okay. Then this delta 2 of Z1 minus Z2. Okay. And then there will be this 1 over 2 pi integration over 0 to infinity d of, say suppose I have done the E1 integral, so it should be like d of E2 delta 1 star plus delta 2 minus, actually it will be 3, because actually from here you will see that from here 1 minute plus 1, yeah, from here actually you see that actually from here actually 1 over some factor of E will come, and that will make you this kind of thing dE2 into this thing. Sorry, dE2 into E2 to be this thing, right? Yeah. Okay. So this calculation I am not doing explicitly, but this is what will happen. Now this is not in general convergent, but actually if you choose delta 1 equals to 1 plus I lambda, okay, then you can actually get a delta function from this integral. Okay. So this integral, if you choose a delta equals to 1 plus I lambda, then this particular integral, it will look like something like this, dE2 to the I of something, no, it's okay, I of lambda 2 minus lambda 1 minus 1, right, and that is our delta function 2 pi delta of lambda 2 minus lambda 1. So now you see that if I choose this n delta 1 Z1 bar, this normalization factor as 1 over 1 plus Z1 bar to the delta 1 plus, then this thing and this thing will cancel, and from here you are getting 2 pi into delta of that thing. So hence the inner product is that is given by delta of lambda 1 minus lambda 2 delta 2 of Z1 minus Z2. Okay. So you see you have to choose delta equals to 1 plus I lambda. Otherwise, I mean for this delta function normalizable basis actually. Okay. Oh, sorry, delta of sigma, thank you. This delta of sigma 1, sigma 2 here also, right? Yeah. This is something called the continuous principal series representation of Lorentz group. Okay. So thus we conclude that this delta sigma ZZ bar, okay, you can also show that u lambda delta sigma z z, suppose u sigma delta 1 sigma 1 z1 z bar 1, then u of lambda delta 2 sigma 2 z2 z bar 2. This first bracket meaning the inner product, that is nothing but delta 1 sigma 1 z1 z1 bar comma delta 2 sigma 2 z2 z bar 2. So this is a unitary transformation basically. So thus I conclude that these states delta sigma z z bar, they form a unitary representation of the SL2C given that delta equals to 1 plus I lambda. So this is my conclusion. Okay.
So what we are calling boost is actually not a boost, is also boost plus rotation.
What I am calling boost is boost. Why rotation has to be mixed with that? I mean under rotation around third axis, this state is getting. I mean the thing is that actually it is an eigenstate of the rotation also, rotation around third axis. That's why it is an eigenstate of the rotation around third axis. It is an eigenstate of the boost along third axis.
No, I mean, so if I boost this delta into theta delta p,
Huh?
I mean, is delta equal to 1 plus I lambda?
Huh? Oh, you are saying that since delta is complex, so somehow you are like, but the transformation comes from like, yeah, I mean it is not like you can mix it with this delta complex number, right? I mean like transformation is a transformation on the state actually. I mean transformation. I mean like on the momentum, say for example. Okay, so the same thing you can do for creation and the annihilation operator as well. So the creation and the annihilation operators, say for example.
So naively, when one uses this little group induced representation, so what you get ultimately are the states that are irreducible representations of Poincare group. But here you've got SL.
Here I have only talked about SL2C. The translation I'll talk about later. Translation I'll talk. I mean just 5 or 10 minutes later. Okay. So I just want to show you the transformation of the creation and the annihilation operator. Say for example the creation operator in the Fock space. So let me write it in this way. So now if you make a Lorentz transformation here, u of lambda, u lambda inverse, this transforms like e to the I sigma, say phi, the angle, a dagger, lambda p, comma sigma. Okay, this you know from the Fock space transformation, right? Now you can similarly Mellin transform this this creation operator, and you call something like a, or let's say o dagger, okay, delta comma sigma z bar, that you call it something like, okay, I am not writing the normalization factor, okay. So this will be something like 0 to infinity dE e to the delta minus 1, and then this a dagger p comma sigma, okay. And similarly you can calculate the SL2C transformation of this object o dagger delta comma sigma, you can see that it will also transform in the same way. So del of lambda z by del z to the h, which is nothing but 1 over Cz plus d to the power 2h, del of lambda z bar del z bar to the h bar O dagger delta comma sigma lambda z bar. Okay. Like any arbitrary Lorentz transformation. This is the transformation property of the creation operator, right? I mean, if you remember, the u lambda acting on p comma sigma, that I think was giving you e to the I sigma of phi lambda of p comma sigma, right? Right? Now actually you can write this as u of lambda a dagger p comma sigma u lambda inverse u lambda acting on vacuum. Here also I think you can write in that way, phi a dagger lambda p comma sigma vacuum, right? And this vacuum is invariant under u lambda. So you see, like u lambda a dagger u lambda inverse is given by this transformation.
So you wrote this equilibrium C sigma sigma.
That's already diagonal.
Yes, yes. Actually, this state for massless particle, this is diagonal under this Lorentz transformation. Okay. So this is the this is the actually Lorentz transformation property of the Mellin transformed creation operator. Okay. Similar thing you can do for annihilation operator as well. Okay. So now suppose you write an S matrix. Okay. So S, say for example, M goes to N, and this is for example say P I sigma I, okay, and then this say Pj sigma j, okay. So this is like a capital M number of particles are getting scattered to like capital N number of particles, okay. So this thing, where this j runs from 1 to capital M and this I runs from capital M plus 1 to N. So this thing you can write in this way. So the vacuum, and then there should be this A of out state, then say P
SNM is matrix element.
this is the scattering matrix element. Yeah. There is this product I equals to n plus 1 to n. Then there is this product j equals to 1 to capital N, A dagger in say P of j comma sigma of j 0, right? This is the S matrix element, you can write it in that way. And now you make a Mellin transformation, and I am calling that amplitude to a Mellin amplitude m plus n. So it will depend on all these deltas, okay. So delta 1 to delta m plus n. It will depend on the sigmas, so sigma 1 to sigma m plus n, and then it will depend all these z and all the z bars. Okay. So that thing is like a Mellin transformation, like 0 to infinity, product of I equals to m plus 1 to n dei to the delta I minus 1, then product 0 to infinity, product of j equals to 1 to capital M dej ej to the delta j minus 1, okay. Then this thing, this 0, product of A and product of A dagger, A out, A dagger in. Okay. This is just I have made a Mellin transformation. Now,
This 0. So that was vacuum state, right?
That is the vacuum
you
state.
only Mellin transform the operator.
Or the creation and the
But
annihilation
why not
operators.
why not the in states and out state in Mellin space?
Explicitly in and out is written here, right?
No. But this in and out means this 0 0 like. The
Are you
vacuum
saying that
state,
okay?
right?
You are saying
Yeah, this should
yeah.
also have some z equals to 0, z equals to 0, and then some.
You want me to write in this way?
Mellin transformation.
Yeah. So the states will also the vacuum state will also Mellin transform, right?
No, Mellin transformation is
I
just
don't
about
understand.
some changing energy of
Why?
operator.
Vacuum state should Mellin transform. Okay, I don't think so. I don't. Okay, I don't think so.
Vacuum state is zero energy, right? Doesn't make sense.
Okay. So the Mellin transformation. So the Mellin transformation, for example, the first all the A's here, it will take you this operator, Mellin transformed operator. Okay. So then then all the A dagger also, it will take you this O dagger, Mellin transformed O dagger. So it will look like something like this. So 0, and then all these O out, product of O out, product of O dagger in. Okay. Now, if you make an SL2C transformation on this amplitude, so then all these object, let me write it actually. Okay, so now if you make an SL2C transformation of these object, this A tilde m plus n. Okay, so let me call this some Mellin transform A tilde prime m plus n. Okay, or rather let me write it in this way. So A tilde m plus n, this is like say vacuum. Now you make a Mellin transformation this way, u lambda say O out, this is delta 1 sigma 1 z1 comma z1 bar, u lambda say inverse u lambda, then again this O out to something like this, and then again for all these things like for in operator, so u lambda O dagger in delta something is wrong, it should be like m plus 1, right? M plus 1, all these things should be like m plus 1. Okay. Similarly, if you do it delta 1 sigma 1 z1 bar u of lambda inverse like this. Okay. Then so the vacuum is invariant under this u lambda, then 0, and this u lambda inverse, right? No, I think this is fine, right? Yeah, this is fine. So now this this u of lambda O out u of lambda inverse that I have just calculated. So they transform like del of, so I can just take that out. So they transform like del of lambda z1 del of z1 to the power h1. So I can write it as I, and then del lambda z bar I del z bar I h bar I. So there is a product I equals to 1 to I equals to m plus 1 to n, and then there is again another product j equals to 1 to m del lambda zj by del zj to the power hj, and then del lambda z bar j by del z bar j to the power h bar j, and this thing will be like 0, product of I equals to 1 m plus 1 to n, then this O out delta sigma will remain same, z will be like lambda z I lambda z bar I, and then there is this like product j equals to 1 to capital M O dagger in delta of j sigma of j lambda of zj lambda of z bar j 0. Okay. Yeah. So you see, I mean, like this is like a transformation property of an m plus n point correlator in conformal field theory. Okay. So that's why the scattering amplitude in Fock space basis, they actually are getting mapped to, they are like behaving like a correlator on the celestial sphere. Okay. Okay. So let me now tell about this translation thing. So you see this O of, for example, you take the creation operator. So 0 to infinity dE e to the delta minus 1. Say for example you are taking the creation operator A dagger p comma sigma, okay, and you are Mellin transforming it. So here you will get O dagger delta comma sigma z comma z bar. Okay, so you are taking a creation operator in the Fock space and you are Mellin transforming it. Now I want to see what is the translation, I mean what is the behavior of this operator under the translation, okay, the fourth translation, the global translation. So to do that I will apply the translation operator e to the minus I, say L dot capital P. Capital P is the generator for the translation, the 4 momentum operator, okay, and then this O dagger delta comma sigma z z bar, okay. So this transformation it will hit directly on this A dagger p comma sigma, okay. So 0 to infinity e to the minus I L dot p A dagger p comma sigma e to the I L p dot L dot p, okay. Now under the translation how does this behave? So this will give you 0 to infinity dE e to the delta minus 1. So it will simply give you e to the minus I small l dot p. L is any 4 vector, okay. I mean the 4 vector, I mean like the amount of translation that I am making. So this will simply transform like this A dagger p comma sigma, okay. Now what you can do, this e to the IL p dot L dot p, that actually, okay, so for example the p that I have written it something like e into 1 comma all the functions of z and z bar, right. So this thing I am writing it as e into q mu, okay. So I am just taking like e out of this thing, I am just p mu I am writing it as e q mu, okay. So then this thing will look like e to the 0 to infinity dE e to the delta minus 1 and then e to the minus I L dot e into q, okay, and then this A dagger p comma sigma. So dE e to the delta minus 1, this is like, okay, this is like sum over n equals to 0 to infinity minus I L dot q divided by factorial n. Okay.
Could you explain once again what happened to the e to the power IL dot q?
This term, this term, this is the translation property of the Fock space,
In the next line, like
this one, right. So I am saying that this is the translation property of the Fock space creation operator. Under translation, there is simply just a phase factor, nothing else, because this is an like eigen operator of the translation, you can say. Commute with the p mu, actually, something like that mostly. Yeah. Okay. Okay. Now you can take this minus I L dot Q n factor, all this factor outside, and you can write this as summation over n equals to 0 to infinity by n factorial 0 to infinity dE e to the delta plus n minus 1, and then this a dagger e comma sigma. Okay, and this thing is something like this thing, something like O dagger delta plus n comma sigma z z bar. Okay, so you can introduce an operator. So you can introduce an operator, say curly p, whose job is like to increase the dimension of this particular operator is by 1 unit. Then you can write this as p to the n O dagger delta comma sigma z z bar. So then you can write this as some e to the minus I L dot Q some p acting on this O dagger delta comma sigma z z bar. So you see that under translation, the dimension of the operator is just changing, it is shifting by some integer numbers. Okay, and there is a factor of z and z bar. This is just under the global translation. I mean, the super translation is like generalizing this L to some any arbitrary function of z bar. So under super translation also that thing will happen. So till this point, if you have any question, you can ask. See, I mean, like I have just showed you that I just got this Mellin operator or this SL2C actually this conformal primary operator, and the delta for those conformal primary operator is actually 1 plus I lambda. So the next thing that I want to show is, I mean, like, okay, so this Mellin transformation, I mean, like this particular Mellin transformation, it can give you any so it can, so this particular Mellin transformation can give you operator of any delta given that integral is convergent. So that so now actually the thing that I wanted to show is that suppose your delta don't lie on the principal series 1 plus I lambda. Okay, so then can you get those delta from these principal series deltas? Okay, so that is the thing. For example, the soft operators in the conformal basis, the soft operators, for example, the leading soft operator. For leading soft operator, the delta is actually 1. Okay. For example, the subleading operator, delta equals to 0. For sub-subleading operator, delta equals to minus 1. So you may ask like how, like if I can get this sort of primary operators from the principal series, and I will share my note. So these actually, so you see, by making this SL2C transformation, and I demanded that those primary states, so they should, they should form a delta function normalizable basis. If I make this demand, then my delta has to be like 1 plus I lambda, right? But the 2D theory that lives on the celestial sphere that theory actually has other operators with delta equals to some other values, not 1 plus I lambda. Okay. Now, my question is that if this is a complete basis, then those operators can be like obtained from this basis itself, right? So that is what actually I wanted to show, but actually you can like believe me ki that can be done, and you can get all those soft operators starting from this principal series operator itself. Okay. And then after that, what I wanted to show, that I think I have to show, is that you see these soft theorems in energy space. So yes.
So in the correlator that you wrote, right, this AM plus N,
Uh,
the amplitude that and you're interpreting.
this you can treat as a discussion session. Okay, I mean like okay, yeah.
So the correlator that you're writing down.
Hmm.
So you have two types of operators: this O out and the O ins.
Yes.
And they both are Z set. So you're saying that they are like a safety correlator, but don't you have to impose something like crossing symmetry or something to like, because this, so Z going to 0 here is not the Z going to 0 there, right? Like
That is something called the antipodal matching or things like that.
Right.
So I mean like in the energy space, the soft theorem goes like 1 over omega S0, then omega to the 0 S1. I'm not like considering the log omega term. So these things. So what I want to show is that in delta space, I mean like in Mellin space, so these things actually like correspond to some pole in delta. So the first thing will correspond to a pole in delta equals to 1. Then the second thing will correspond to a pole at delta equals to 0. So something like that. So that actually I want to show you. Okay. And then actually I will just directly start from the conformal soft theorems. I will talk about some symmetries, like the SL2C symmetries, how we can get them from the conformal soft theorems. Then I will talk about the OPs. Okay, I mean like how using the symmetry of the 2D theory, you can compute the OP, and you can actually relate them to the bulk. So this is completely a concrete holographic calculation that will be okay. So at least that thing I want to do. And then I don't think that if I get time, then only I will talk about W1 plus infinity symmetry, or I won't talk about at all. If
Just one question. So I mean, this H,
hmm.
these are, I mean, when you talk about SL2C safety, these are like related to L0, right?
Yes.
But here it's related to, I mean, this delta. So how is it, where, I mean, now there's the Hamiltonian thing, right? There's a boost and this rotation.
Hamiltonian kind of thing, matlab actually this is
I mean, this H is like L0 eigenvalue, right?
yes.
Here, what is the analog? I mean, but here there is no L0, there is K3 and J3.
No, but you can map those operators to L0, right? I think L0, I mean like actually all these L0, L1, L minus 1 and L bar 0. Okay, that I think I have to like think. I mean, so L0 actually it should be something like, it is some combination of J3 and K3, J3 plus minus, I mean some combination of J3 and K3. Okay. So you see, I mean like this is actually again will diagonalize the L0, these operators, I think, yeah. Yes. No, boost, okay. Say it again. Boost generator is Hermitian. Yeah, I think every Lorentz symmetry generator should be Hermitian.
So it should have real eigenvalues. This data is your K3 eigenvalue that we saw from the 2D.
No, actually you see here the things are different. For example, this adjointness is also different from the usual CFT. I mean, so yeah, I mean like this, actually this, since these deltas are complex actually, I mean, so you cannot say that these things are actually Hermitian. I mean like, I mean for example in CFT, See, in CFT, I think the adjointness condition L dagger n is defined something like L of minus n, right? If I remember it correctly. But here actually it will not be the case. I think here it will be something like L dagger n should be related to minus L bar of n, something like that. So things are different. I mean, like though some similarity is there with the 2D CFT, but there are a lot of differences. Okay.
If you take shadow transform of like, so right now in the inner product that is defined is between two states, but now if you take the inner product between a shadow transform and then the state, then it will then you can show that this property holds, and corresponding in 2D CFT you can define something called BPZ inner product there. So, but it will be indefinite. So that's like that's the hallmark of it's like non-unitary conformal field theory because there's a negative dimension. So yeah, it's still this. It's not yeah, that's still the work is complete. There's a recent paper. This is 2021. This one paper. So that defined these things like BPZ inner product and all that. Okay. But basically, you just have to take the shadow transform of the primary state and take the inner product of it with primary state, and then you will be able to show that ln dagger goes to n minus.
The main doubt problem was that we are getting unitary representation.
No, but still I think data will be complex there, right?
Delta is complex, but the
So when delta is complex, how will you like this radial quantization thing, like saying that this is the Hamiltonian? That is, I mean, so that's what I'm saying. That theory is, I think, still like about unitarity we cannot say anything. Yeah. I mean, yeah. I mean, like.
Yeah, but this is not how you define an inner product. Like,
I think his question is very simple. Like if you take the state delta sigma zz bar, you add the u of b3 on it, you will e to the eta delta times that state. Delta is complex, whereas on the left hand side you had you would have expected real eigenvalues for this thing, but now you have something complex. He's asking how do you reconcile this? Like,
No, actually, I think what he's trying to say is that, I mean, like in usual CFT, what we do is that we just take that dilatation operator as the Hamiltonian because that has a like relation with that, and the deltas are real there. So they are basically the eigenvalue. You cannot do that radial quantization thing. I mean, you can do that, but I mean, like these deltas are complex actually. This basis form a unitary representation of the Lorentz group. Yes. Yeah, the basis is forming the unitary representation of the Lorentz group does not tell you that the theory is unitary because the evolution, that may not be like a unitary evolution.
also, isn't it to do with this bulk is Lorentzian and the boundary is Euclidean? So that is sort of also creates some problems. Rather than ADS-CFT, both were Euclidean, but here because there is this subtle thing that the bulk is Lorentzian and the boundary is Euclidean, you have to. It's not straightforward as an ADS-CFT. The interpretation.
It is not straightforward as ADS-CFT. That is true, but yeah, I mean like